Hey everybody, in this video we're going to talk about how to explain a substance's physical properties by talking about the types of intermolecular forces that substance will experience. In this case, we're going to be examining CH4, otherwise known as methane, comparing it to CBr4, otherwise known as carbon tetrabromide, and we're going to be trying to decide or predict which of these is probably going to have the higher boiling point. Just like with pretty much all cases involving molecules, which these are, by the way, carbon is a nonmetal, hydrogen also a nonmetal. These are all nonmetals, which means we're talking about molecules here. Everything goes back to the Lewis structure and the shapes of those molecules. So that's the first thing we need to do. Luckily, both of these molecules are very similar. They both have carbon at the center in this tetrahedral arrangement. So let's go ahead and draw those first really quick. Now, one thing should jump out at you right away when you're looking at both of these molecules, and that is the fact that they're perfectly symmetrical. The bonds here between carbon and hydrogen and carbon and bromine might be a little bit polar, but that doesn't matter anyway because they're perfectly evenly spaced in all directions around that central atom. In other words, what we end up with is two molecules that are both nonpolar. And that's what you really need to know when it comes to analyzing molecules. In other words, these substances will have no net dipole is the proper way to say that, and that's key, so we want to make sure to write that down and keep track of what I know about these two things so far. Now that is really important to know because now that I know they're both nonpolar, I can talk about the types of intermolecular forces that methane molecules are going to experience between one another. Same thing with CBr4. For nonpolar molecules, there is only one type of intermolecular force that they're going to be attracted to each other with, and that is a London dispersion force. Since that takes a long time to write, I'm going to be a little bit lazy and just mark that down as LDF, and I'm going to clarify LDF only because as nonpolar molecules, that is the only force that is going to occur between these molecules. In other words, no dipole-dipoles, no hydrogen bonds, no nothing else. The next step is going to be to compare the strengths of these London dispersion forces. To do that, when it comes to LDF, there's really two considerations, and I'm going to mark those out, number 1 and number 2, on the left part of the video screen. The first one is the sizes of the electron clouds of the atoms involved. You can think about that as sort of like the atomic radius. This is going to tell you about something called polarizability of those molecules themselves. The second factor is chain length, which has more to do with surface area, and you have to really consider both of these things. And let's actually start with the chain length comparisons because these molecules are not chains. It's just one single carbon surrounded by some hydrogens, one single carbon surrounded by some bromines. So when your molecules look like this, when it's just like one single clear central atom, you do not have a chain-based molecule. So we don't really even have to worry about that factor as far as the strengths of these LDFs. So I'm going to cross it off and essentially not pay attention to that at all. I do have, however, some extreme differences in electron cloud size. Hydrogen atoms are these super teeny tiny. They only fill electrons to the 1s orbital atoms, whereas bromine atoms are huge. Their radii is way larger. If you wrote out the electron configuration of bromine, you'd see that it fills up to like the 4p's, right? So very high energy level. Bromine is much farther down on the periodic table. All of these things tell you that the CH4, specifically the hydrogens in the CH4, are much smaller electron clouds, whereas the CBr4, specifically the bromines, have a much larger set of electron clouds. And that's key for LDF strength because as soon as you know that, you've got your answer. Large electron clouds have this capability or have this thing that they can do, and that is called being polarized. And the bigger that electron cloud is, the more polarizable that cloud is going to be. The opposite is true, of course, for smaller electron clouds. That is going to be much less polarizable. At this point, I pretty much have the answer to my question. Here's how it works. Once you know which of these atoms has the more polarizable electron cloud, you also know which of these molecules, I should say, which of these molecules will have the stronger LDFs, and that's the CBr4. The way it works is a larger, more polarizable electron cloud is going to give you stronger London dispersion forces. Over here with CH4, we're going to have weaker London dispersion forces. And once you know the strengths of the attractions that exist between CH4s or between CBr4s, you can make your predictions about property. And you can do that because there's lots of specific properties that stronger attractions are going to cause. Things like being a liquid at room temperature, or maybe even a solid at room temperature. A lot of properties are going to be elevated, like higher melting points. Higher enthalpies of vaporization is a common one, and in this particular case, the one we were trying to analyze from the beginning, a higher boiling point. So I can label that CBr4 is probably going to have the higher boiling point, or CH4 is probably going to have the lower boiling point, and my prediction has been made. That also wraps it up for this video on explaining properties with intermolecular forces. Thanks a lot for watching.